Welcome back to modern algebra. We're still looking at group homomorphisms and group isomorphisms, and now we come to a very important theorem about those concepts called the fundamental homomorphism theorem for groups. And the rough idea, the intuitive idea of what this theorem does is it says, given any group homomorphism, which preserves structure but might not be one-to-one, might not be onto, we will build from that homomorphism a related group isomorphism. It is one-to-one and onto. And this construction that is used in the theorem to do this will shed new light on quotient groups and cosets and what those things really mean. Intuitively, and where they come from. And this theorem just ends up being fundamental, as the name states, in the further study of groups. So it's certainly a keystone of our coverage of group theory in this introductory course. So let me remind you of the picture you could draw for a group homomorphism. So maybe we have a group here, G, the domain, and another group, K, the codomain, of some function that's a group homomorphism, F, and you can imagine all these arrows going across. And the thing about this function is, well, there's two things. We kind of like one-to-one onto functions, but not every function is one-to-one onto. F might not be onto, for example. But even if it's not, it's going to have what we call the image of F. Let's call that M. The set of all codomain values that actually occur as function values. So this entire group G is being sent into this image, and there could be other stuff over here that's outside the image, plus stuff that's inside. All right. And we've seen that this image is a subgroup of K. We proved that earlier. And then on the other hand, so one thing you could do, if you wanted to make it be onto, where F goes from G to K initially, it's not onto, you could just shrink the codomain down to M and make a new function with that codomain, and that would just automatically be onto. So that's not hard to achieve if you're willing to change the codomain. But what about being one-to-one? So that's a harder issue. And recall, we had this thing called the kernel. So let's call it H for short. And we saw that this kernel is always a normal subgroup of G. We proved that. And of course, it contains E, the identity of G. And over here somewhere is the identity of K. And everything in this kernel, which could have a lot more stuff in it than just E, but everything by definition in the kernel gets sent to the E of K. The kernel of F is the set of all x in G such that f of x is equal to E sub K. That was the definition of it. All right, and the trouble is, the way I drew it, that's not one-to-one if there's more stuff in the kernel. We also proved f is one-to-one if and only if the kernel consists of just E. But what tends to happen is that there's more stuff in there, And then you get all sorts of these other clumps of elements that all map to the same thing under this F. So maybe the stuff in this clump all goes here. And the stuff in the brown clump, there could be lots of points here. Maybe that all goes here. And maybe the blue elements all go to here. Sorry, the sort of a messy picture there. And then the idea would be, well, there's all this collisions, and if you thought of these individual guys, these clumps, as just single objects that F maps over, then that would be one-to-one. If this one thing, this blue object goes here, and the brown object goes there, and so on, and the kernel goes to E, you sort of collapsed away all the collisions and you forced it to be one-to-one. That's the intuition. And the really remarkable thing is that these colored clumps that do this end up being the cosets of the kernel. As we will see eventually. And in some sense, this picture leads you naturally to consider the set of all cosets, the set of all clumps, which we call G over H. Recall that as well. That general definition for any normal subgroup of G, G slash H, was the set of all of these right cosets, or equivalently left cosets. And the important thing about these cosets, well, one of the important things is when are they equal? H star x is equal to H star y if and only if x star y inverse belongs to H. That was the right coset equality here. All right, so I haven't justified this picture, but we will. So the theorem will show that this is actually what happens, and these clumps that are forming from the homomorphism magically create the G slash H quotient set and can give you what you want. Okay, so now I'm ready to state the theorem. So let G and K be any groups, G star and K dot if you want. And we'll have an arbitrary group homomorphism. Homomorphism with image, let's call the image M, as in the picture, which is a subgroup of K. And the kernel, we'll call that H, which is a normal subgroup of G. And now I will tell you about an isomorphism, which I'll call F naught. And the isomorphism will start at the quotient group G slash H, and its codomain will be M. So new domain and codomain. And the formula for F naught, because G slash H is a set of cosets, I have to tell you, where is this new function going to send a coset H star X? And by definition, it's going to send that coset to F of X. So it's related to F, so I call it F naught. And the assertion is that this is a well-defined group isomorphism. Between its domain and codomain. So to say that symbolically, just to summarize what the theorem says, it's saying that G mod or the quotient group by the kernel of F is an isomorphic group to the image of F. Via the isomorphism F naught. There's a specific formula for it that's right here. And again, all that's really happening in the picture is it's saying for all these blue guys are going to map to the same guy in this coset H star X. If this is like X. And so just send the whole coset over to that same point F of X that X was mapped to. And there's all sorts of stuff that has to be checked, but that's the intuition for what's happening here. All right, so this is fundamental homomorphism theorem for groups. This is a statement of it. All right, so let's prove it. And for the proof, we have to check all the stuff. We have to show it's well-defined. We have to check it's a group homomorphism. We have to check it's one-to-one. We have to check it's onto. So 4 parts. So is F not well-defined? And what does that mean? It means that, let's write down what we have to prove. We have to prove that whatever names we choose, so for all x, y, and g, if we take the same input and give it 2 different names, so instead of h star x, maybe h star y is another name for the same coset, then is it really true that the output f of x is the same as the output f of y? That's the first task. All right, so let's fix arbitrary x, y, and g. Let's assume h star x is equal to h star y. And let's prove that f of x is equal to f of y. All right, now let's see. I wrote down one of the conditions in the right coset equality theorem, but here it might be easier to use one of the other conditions. All the conditions that we have. So if h star x is equal to h star y, then you could say that y is in h star x, which in turn means that y equals little h star little x for some h in h. Now, what was h? H is the kernel. The kernel of f. So what does that mean? That means that f of little h is e sub k. So little h is over here somewhere. And then, well, then what's f of y? F of y is f of h star x. F is a homomorphism. So that's f of h star f of x. F of h is e sub k. And so by the identity property, I get f of x. So f of y is equal to f of x. So it is well defined. All right, great. Let's next check, is f naught a group homomorphism? Does it preserve the operations? Well, let's check. So now let's fix 2 elements of g slash h. Maybe we could call them h star a and h star b in g slash h. A and b come from capital G. And let's check that f naught of the product of those cosets is really equal to f naught of h star a dot f naught of h star b. All right, I've got too many dots. There's a huge dot for the quotient group operation and another dot for the operation in K, but whatever. Well, let's compute it. If the dot's on the inside, as it is on the original left side expression, I have to do the operation in the quotient group. To multiply the cosets, remember we're going to just get a new coset, h star quantity a star b, by definition of g over h. That's how you multiply cosets. And then f naught, which is well defined, so I don't have to worry about that again. It's given being right here. Whatever this x is, to get the answer, I say the original f of that x. In this case, x is a star b. So I'm going to get f of a star b. That's the definition of f naught. It's how it was defined in the theorem statement. And f is a homomorphism. We know that already. F as opposed to f naught. So I get f of a star f of b. Or rather dot, whatever the operation symbol is in K. And then finally, that's, again by definition of f naught, that is f naught of h star a, that's f of a. And then we have dot f naught of h star b. So that's the definition of f naught. And we reached the other side of what we were trying to prove. So we have this group homomorphism well defined. And I have to erase stuff. All right, so third, we have to check that this new function, f naught, is it actually onto. And this is the part where the fact that we changed the codomain to M. I guess I erased the picture, but remember that we shrunk the oval on the right side of the picture, which used to be K. We said, no, we're just going to make it be M, the image. That's going to basically make this thing be onto. But let's write down what we have to prove. So we have to prove that for every z in M, codomain of this new function, there exists an x in G, or how to say it. There exists a coset, if you like. There exists an h star x in G slash h, such that f naught of h star x is actually equal to z. Spelling out the definition of onto. So, well, we can fix an arbitrary z in M, which is, recall that the M is the image of f, the original f. Well, and what's the image? So it's the set of all function values. So by definition of image, there is an x in G. Maybe call it x naught if you want. An x naught in G, where f of x naught is C. And then, well, we get a coset. H star x naught is one of the things in G slash H. It's a right coset of H coming from an element of G. So we have that. And when you do f naught to H star x naught, you get, by definition, you get f of x naught, which is C. So we did it. So basically F naught, and just as a sort of side note, this basically proves that the image of F naught is exactly the same as the image of F, just as a little consequence of this proof here, which shouldn't be a shock based on this formula here. But in particular, it's onto is what we needed. It's onto. And then the last thing we have to check is F naught 1 to 1? The original function likely wasn't, because they had this kernel. What did we call the kernel? H. That multiple things in the kernel were all going to E. But this quotient group construction basically gets around that. But let's write the definition again. So what do we have to prove? We have to prove that if you give me any two cosets, let's call them, I guess, H star A and H star B again. If they map to the same thing under F naught, then not that they're equal, not that A and B are equal, but that the cosets are equal. Right? Coset equality theorem yet again. All right, so let's do that. So let's fix arbitrary A, B, and G, if you like, because every coset is named by elements of G. Let's assume that F naught of H star A is equal to F naught of H star B. And let's prove that H star A is equal to H star B. So, and here's where I can finally maybe use this right coset equality theorem. Let's immediately rewrite that goal, an equality of cosets, by saying, okay, I have to prove that A star B inverse is in H. Okay. Well, what does that mean? So first of all, let's keep rewriting the goal for a second. So because H is the kernel, we have to prove that F of A star B inverse is equal to E sub K by definition of H, namely the kernel of F. So I'm just rewriting the goal even more. And what we've got in our assumption, we're calling the definition of F naught. We actually assumed that F of A is equal to F of B. But then, by a trick we've seen before, if you multiply both sides in K by F of B inverse, you get E sub K. And then you move the inverse inside. You get F of B inverse is equal to E sub K. And then you use the fact that F is a homomorphism. To get that F of A star B inverse is equal to E sub K, which is exactly what the rewritten goal is. So we did it. All right, so that's the end of the proof. We've proved the fundamental homomorphism theorem. All right. All right, so just a few more comments related to the theorem, and we'll do a bunch of examples later. I've rewritten the theorem here, and I've redrawn the sort of the arrow diagram type picture for part of it. And I just want to go back and look at this coset idea a little bit more. So we have sort of the kernel down here. But now I'm sort of interested in a general coset of the kernel. Maybe this is H star X, where X is some point, or what do I want to call it? I call it X naught. So x naught is in that coset, and there's a whole bunch of other stuff in there too. And x naught is going to be sent by f to some point y naught in the image. So let's say it like this. So let y naught be in the image of f, and therefore y naught must be f of x naught for some x naught in G. And then sort of another little mini theorem that's very closely connected to what we just did is that then this coset h star x naught, say fact, the coset h star x naught, which you could also write as the left coset, they're equal because h is normal in G. So this coset, this collection of objects in G, is exactly the set of all z in G that map to that point. The set of all z in G with f of z is equal to y naught. And I'll just sort of quickly prove that, because it's almost the same thing as part of the argument we just did. So let's fix a z in G, and I'll basically say that z satisfies this condition if and only if z is in there. So f of z is equal to y naught if and only if z is in h star x naught. And this is just sort of a parenthetical remark about the left cosets. Well, let's try a chain proof, a chain of known if and only ifs that goes from the left side to the right side. So f of z is equal to y naught, which is this condition. If and only if, well, that means that f of z is equal to f of x naught. And then we do the same thing we just did. We sort of dot by f of x naught inverse. And I'll condense some steps here. So by homomorphism properties, that changes into the fact that z dot x naught inverse, f of z dot x naught inverse is equal to bk. And that means that's equivalent to z dot x naught inverse belonging to the kernel of f, because it goes to E when we apply f. And that's equivalent, well, kernel of f is h. And, well, wait, that's the right coset equality theorem. So z times x naught inverse on the right belonging to h is the same thing as saying that h star z is equal to h star x naught. Or better, I could have also just immediately recalled another property from the long list of conclusions of the right coset equality theorem. This is saying, as needed, that z is a member of h star x naught. So, and sometimes this is called the fiber of f over y naught. Instead of all inputs that map to y naught when you do the function, and what we have now proved is that this right coset of h, of the kernel, which is equal to the left coset, is the fiber. It is the set of all things in the domain that map to this one particular element of the image. And again, this is the retroactive intuition. Why would anybody come up with cosets? Why would anyone come up with the quotient group? And the answer essentially is, if you looked at enough group homomorphisms and drew their arrow diagrams, you would eventually notice these fibers. There's a whole bunch of them, one for each coset. The kernel is the fiber of E, everything mapping to E, but then everything mapping to, these other points gives you the other cosets of H, the cosets of the kernel. All right, and then if you look at just these lumps that I've formed, the set of all these clumps is the G/H, and it's giving you the isomorphism F0. So I hope that gives you a little bit of intuition for what that quotient group construction and the coset constructions actually mean. All right, so that's the end of the proofs. We'll come back in the next segment and look at examples of using the fundamental homomorphism theorem for groups.